1 week from Friday. Oh, we will have a help session. We do those on Thursday or Friday? I forget. We do them on Friday. So we'll have a help session on Friday, but we won't have the one the next week. Yeah.
Okay, so if someone has
No, it depends on your requirements. But if you're a biology major, you're required to take 8 hours of physics. 4 hours this semester and 4 hours next semester. The lab next semester is fun. You build circuits and you do license contracts. What did you just say?
Probably not.
No, it is fun.
You're going to be really excited.
There's no offering of Physics Lab 1 next semester. The lab that you're taking this semester is not offered next semester. What are we doing? We have an exam coming up. Let's try this question. This is a lot like the sample, or the example we left off with last time. What is it? Is everything okay? What is it? Oh, your lives. Let's do this question. If you can't see the options, if you don't have your workbook, you can just look on the options for the next person. All right, let's do about 10 more seconds, okay? I'll stop at 240. 240. A few more seconds. Just guess if you're not sure. All right. Okay, so this one is a lot like the one we did last time, except the numbers are a little bit different. A is the right answer. The way you do these, and the way you do all these, in fact, and you'll have a couple on your test, 2 or 3 like this, where you say that the initial momentum in the system is equal to the final momentum in the system. Remember, these are vector quantities, so you have to be careful with your signs. Our initial momentum is just the ball. It's going to be the mass of the ball times the initial velocity of the ball. And that's going to equal the final momentum. It says that the ball... well, it doesn't say this, but you assume that the ball goes to rest afterwards. It doesn't say anything about its final velocity. But the final momentum is going to be the mass of White-Goodman times his final velocity. And so the mass of the ball is 0.5 kilogram. The speed of the ball is 10 meters per second. I'm going to put a plus here because it's going in the positive x direction. And then that's equal to 100 kilograms times the velocity, the final velocity of White-Goodman. and you solve that and you get 5 divided by 100, which is 0.05. And it is positive. That means it's to the right. Okay? All right, we'll do some more of these in just a bit. But let's look at two different types of collisions. So far in this chapter, we haven't had much. We had impulse and momentum. That's our whole F is delta P over delta T. And so if you know an object's change in momentum, you can figure out the force that is acted upon it. However, you change the amount of time that the force acts, you change the amount of momentum that's imparted to the object. We also looked at collisions. That is when we have two objects that hit one another, and we use the idea that momentum is conserved in order to find the final speed or something about that scenario. And now one more thing, I just want to clarify about two different types of collisions. And in your OpenStax, which is due, when does that thing due anyway? Wednesday. So your OpenStax, which is due on Wednesday, deals a little bit with elastic and inelastic collisions. For the test, you just need to know what is an elastic, what is an inelastic collision. In an elastic collision, momentum and energy are always conserved. In fact, you know what? Momentum is always conserved regardless. It's only energy that's sometimes conserved and sometimes not conserved. So momentum, always conserved. That's why we can use it in these really crazy situations, like when a car runs into a dummy. That even though there are all these weird forces going on, we can still deal with it from a sense of conservation momentum. Energy is sometimes not conserved. But in an elastic collision, the objects bounce off one another, and then there's nothing lost. There's no energy lost. So what type of forces are involved in an elastic collision? And we talked about two different types of forces. What type of forces are involved in an elastic collision where both momentum and energy are conserved? Think back to the previous chapter. We classified forces into two different types. Friction was one, gravitational force is one of those. What type of forces are involved in an elastic collision where energy is conserved? No. What type of forces are involved? Anybody know? Right. What type of forces are involved in an elastic collision? And in an elastic collision, energy and momentum are conserved. Momentum is conserved in all collisions, but particularly in an elastic collision, energy is conserved. So what type of forces conserve energy? Conservative forces, right. So conservative forces conserve energy. Remember, that was from the previous chapter. You do need to know that, by the way, for the test a week from Friday. So these involve conservative forces because energy is conserved. And remember, conservative forces included those field forces. Anytime you have a force where there's no contact between the objects, that's a conservative force. There aren't many examples of elastic collisions in the universe, at least not in everyday life. But what are some examples of elastic collisions? Collisions between objects that conserve energy. Gas particles. That's sort of a big one, that gas particles involve elastic collisions. And we sort of talked about this earlier, how we deal with gas particles and develop thermodynamics. Because we can use this idea that both momentum and energy are conserved. So if you imagine that you have gas particles, they have, slightly positive or negative charge. I'll say that they're slightly positive. If they're headed towards one another, like this, they're going to sort of swerve and miss one another. They're never actually going to touch. And that's why energy is conserved in the interactions between gas particles, because there's never any contact between them. So gas particles, anytime a field force is at play. You can get it out in space too when stars interact, that both energy and momentum are conserved. That's not electric forces, which are field forces, but gravitational forces, which are also field forces. All right, we also approximate some collisions as elastic. Like if a collision between two objects doesn't lose much energy, like it just uses a little bit of energy, we'll approximate that as elastic. So for example, billiard balls, pool balls, those are pretty much an elastic collision because there's not much energy loss. There's a little bit of energy loss to sound, but otherwise there's not a lot of energy. A little bit to heat, but mostly it's an elastic collision. So in elastic collisions, only momentum is conserved, and energy is not conserved. These are most collisions in the universe, all other collisions. So bumping into somebody out in the hallway, elastic or inelastic? Inelastic, right? Because you're making contact, you're losing energy and heat and friction and sound and whatever, deformation. So every other collision, a car running into a tree, that's an inelastic collision because energy and momentum is not, or only momentum is conserved. Now with elastic collisions, we can say two things. We can say that PI is equal to PF, and then also that the initial energy, that is KEI plus PEI, equals KEF plus PEF. And so you can set up, if you have an actual elastic collision where energy is conserved, you can set up both of these equations. Just like we did in Chapter 5 for the energy, and just like we've done in Chapter 6. Except now you have a system where both of these things are conserved, and you have two sets of equations. Actually, you can have 3 or even 4 sets of equations. We're not going to do this here. You might see it. I don't remember if I gave you one in the OpenStax. I don't think I did. I might have, though. But it works exactly the same. You solve this, and you also solve this. Okay, but you won't see elastic collisions on the test, where you have to solve for both the energy and the momentum. All right, I think that's it for this chapter. Oh no, perfectly inelastic. So this is just a type of inelastic collision. Don't be thrown off by it. In fact, it's even easier than the ones that we've done before. It's called perfectly inelastic because the objects actually stick together. They come together, then they stick, and then they move off in the same direction. So if I have two objects in this perfectly inelastic collision, I say PI is equal to PF. Because remember, only momentum is conserved in an inelastic collision. The initial energy is going to be M1 V1I plus M2 V2I. And then that's going to be equal to, look, I'm going to group these together. I'll explain why in just a second. M1 plus M2 times VF. I group these together. This is just like we did before, but I group them together because when they stick together, they're going to have the same speed as they move off into some direction. Okay? If this bothers you, you can write this out. You could write M1 VF plus M2 VF, and it's exactly what we've been doing before. But on a perfectly inelastic collision, it's a lot easier to solve because you only have one final velocity. You don't have two final velocities of the objects moving in different speeds. All right, so the objects stick together upon colliding in a perfectly inelastic collision. So they both have the same final velocity. What's conserved in every collision in the universe? Momentum is conserved in every collision in the universe. Energy, on the other hand, in this case, is not conserved because you have contact between the two objects. And anytime you have contact, energy is not conserved. So momentum is conserved, energy is not conserved. I would expect some questions about elastic or inelastic collisions. What is an elastic, what is an inelastic, and what is an example of each on the test. We'll look back at some of the old exams, you'll get some samples. We might look here in just a bit. But like right now, I think that's the last page there, isn't it? Yeah. Oop. Let's do that. Is that the last page of that chapter? Yeah, let's go to the concept test. All right, a small car and a large truck collide head-on and stick together. Which has the larger momentum change? A small car and a large truck. So they come and they collide head-on, and then they move off, they stick together. Which has the larger momentum change? Now think about the forces that are involved between the large car and the small truck. And then think about our impulse equation, that F equals delta P over delta T. And what does that tell us about the change in momentum? All right, let's do about 10 more seconds. Hey, very good. C is right. They both have the same momentum change. You think about these objects colliding with one another, think back to Newton's third law. If the truck exerts a force on the car, then the car is going to exert that same force on the truck. So we have the same forces that are involved. Remember, F is equal to delta P over delta T. We have the same forces involved. Whatever force the truck exerts on the car exerts on the truck, and vice versa. F is going to be the same for both. Delta T is also the same for both. So they're going to experience a change in momentum that's the same. Now, because the truck has a bigger mass, it's going to experience a change in speed that's what? Bigger or smaller than that for the car? Smaller, right. So the truck has a big mass, so delta V for the truck is going to be smaller. Two boxes, one heavier than the other, usually at rest. Same force for exactly 1 second. Which has more momentum? All right, let's stop at 38. 38. Okay, good. C is right. They're both going to have the same. Because for the same reason. F is delta P over delta T. They got the same force. They got the same time. So they're also going to have the same change in momentum. Which box has the larger velocity after the force acts? So the same force acts for 1 second. Which will have the larger velocity? They both have the same momentum. Which has the larger velocity? All right, I'm going to stop at 30 seconds. 30. Look at y'all. B is right. The lighter one, because it has the same change in momentum, but if the mass is smaller, the change in speed is higher. Or you can think about it in terms of Newton's second law. But really, we've been dealing with Newton's second law, right? That F delta P over delta T, that is Newton's second law. If I have F equals ma, if A goes down, A goes up. Likewise, M delta V over delta T, or delta P over delta T. Those are all expressions of Newton's second law. Hey, what's the difference between a cat and a complex sentence? Never thought about that, have you? What's the difference? You don't know, right? A cat has claws at the end of its paws. Yes, Damien. But a complex sentence has a pause at the end of its paws. You think about that for the rest of the day. So stupid? Is that what somebody said?
Did somebody say that? You said so stupid?
No, no, I thought the answer.
Oh, okay.
Sorry.
Okay, a small beanbag and a bouncy rubber ball are dropped from the same height above the floor. They both have the same mass. Which one will impart the greater impulse when it hits? The beanbag, the rubber ball, or will they impart the same impulse? And remember, that impulse is our change in momentum. Remember, it's just another word for change in momentum. All right, we'll stop at 104. 104. Okay, good. The rubber ball. Why would the rubber ball impart greater momentum or a greater impulse to the floor? What is it about the rubber ball that causes it to impart a greater momentum? And what now? It bounces, right. So if you remember the lady in the car that bounced off the wall, we had two velocities. We had one that was positive and then one that was negative. And so when we calculate our change in momentum, this is our initial, this is our final. Then we have m times negative VF minus m times positive VI. And so you get a number that's twice as big if it bounces off at the same speed. It just makes the change in momentum bigger. Let's try this one. This one's related. And then I have a started point. All right, we'll stop at 40. 40. Okay, good. A is right. It's hailing, because if you think about your umbrella, and you get these raindrops that come onto it, the raindrops, they just sort of hit the umbrella and then they roll off. But if we have hail drops, they hit the umbrella and then they bounce off. And so just like with the bouncy rubber ball, it imparts a greater momentum. And as a result, since F is equal to delta P over delta T, if delta P goes up, then F goes up as well. Hey, listen, I went to a boarding school in high school, math and science school up in Mississippi, and in the dorm, we had like 150 guys living in the dorm, high school guys living in the dorm. And just crazy stuff when you put 150 guys into the same building, especially high school guys. We would do this stuff where we had, we'd take towels. You ever make a rat tail out of a towel? Y'all done this before, right? Made a rat tail. You have to get a nice sort of damp towel, and then you roll it up, and then you can walk around and you can pop people on the behinds with it. Who's done that before? Just 4 of us, right? 5 of us. Okay. So we would make these rat tails, and everybody got really good at using their rat tail. The thing about a rat tail is that you want to swing it out, and then what do? You pull it back. For the same reason here, because if you get both a velocity in that direction and then velocity coming back, if it bounces off of the person's behind, then it makes it a lot more painful. And it can be very painful, am I right? Yes, very, very painful. We should try it one day. We can all make rat tails. But it's very important that you get that recoil velocity. That it just makes it a lot more painful. Right, Mallory? Yes. Okay, so next time you make a rat tail, make sure that you get that velocity there and velocity back, because it increases your change in momentum, and then it increases the force, which is really what you want to do. You want to maximize the force onto the person as much as possible. Okay. Let's try this. All right, let's stop at 30, or 33 maybe. Okay, yes, that's right. So, again, goes back to our Newton's second law. F is delta P over delta T. They have the same momentum. This is the same for both. You have the same force acting on them. And so in order to affect that change in momentum takes the same amount of time. So B is right for this. You'll certainly see some questions like this on the test. Just asking about the relationship here, F is delta P over delta T. Let's try this one. This is a collision problem. And actually, this is a perfectly inelastic collision. Perfect only because they stick together. All right, let's stop at 1 minute. 1 minute. A few more seconds. Okay, B is right. The way you want to do this, we can just sort of work it as we've been doing all the others. VI here is 10 meters per second. We don't know the mass, but it turns out it doesn't really matter. Your initial momentum is equal to your final momentum. The initial momentum is going to be m times 10 meters per second. And the final momentum is going to be m plus m times Vf. So that's 10m equals 2m times Vf. And then the m's cancel, and Vf is equal to 5. The mass doubles, so the speed halves with our conservation of momentum. E is right there. Are any of you that splits into two pieces? Which has the greater momentum? Looking for the magnitude of the momentum. Which has the greater magnitude of momentum? All right, let's stop at 40 seconds. 40. Okay, good. Both are going to have the same momentum. What's the momentum of this guy right here? Is it moving? No, so what's its momentum? 0. It has no momentum at all because it's not moving. Momentum is mass times velocity. If V is 0, it has no momentum. And so when it splits up, I have some momentum in this direction, some in that direction. What's the momentum of this system, the second system? Well, we know that the initial momentum has to equal the final momentum. So what's the momentum of this system? Is 0. So say this guy has plus 5 kilogram meters per second. This guy has what? Minus 5. 0, and 0. But in the second scenario, they're moving. They're just moving in opposite directions, so they have equal and opposite momenta. Which has the greater speed? The big one or the small one? All right, let's stop at 30. Okay, good. B is right. The light one, we know they both have the same momentum. P is equal to mv, and so the one with the smaller mass has the bigger speed, has the bigger velocity. All right, this is another conservation momentum problem. They push off of one another. Amy goes at 6 meters per second, and Gwen goes at which speed? All right, let's stop at 55. 55. Okay, E is right. So initial momentum equals final momentum. Initially, neither one of them is moving, so it's 0. And then the final momentum is going to be, for Amy, 150 pounds. Although we know that's not mass, but I'm just going to leave it as that because it doesn't really matter. The G would cancel out anyway. 150 pounds times -6 meters per second plus 50 pounds times VF for Gwen. And then we solve that for VF. Since she has a third the mass, she has 3 times the speed. It's going to be 18 meters per second. This is very similar problem. Try to just think about it. The mass here, 10, is 1/100th of 1,000. And so, what is going to be the new speed of this flat car? You're doing awesome. Got this down okay? 1D collisions. I'm going to show you a 2D collision. So I'm not going to test you on it, but I just want you to see a 2D collision. And then we'll move on to the next chapter. All right, let's stop at 1 minute. Just a couple more seconds. Okay, good. B is right. 1/2 meter per second to the right. So the long way you work this out, although hopefully you can look at some of these and just think about what the answer is by looking at the relationships. But if you have to work it out, that's okay too. So 0 is equal to 1,000 kilograms times the final velocity of the flat car plus 10 kilograms times let's see, the ball is going in this direction, so it's -50 meters per second. And then I solve this for VF. It's going to be equal to 500 divided by 1,000, just 0.5. And it's positive, so it's to the right. We got one more here. All right, let's stop at 45. 5 more seconds. Okay, good. C is right. Y'all are awesome. It has more kinetic energy than the gun because they have the same momentum. Like when you shoot your gun and there's a bullet that comes out of it, they both have the same momentum because initially the momentum's 0. And just like the uranium nucleus, when they split apart, they have equal and opposite momentum. However, the kinetic energy is a lot different. The recoil velocity of the gun is really small, but the velocity of the bullet is really big. And since I have that 1/2 mv squared, then if the bigger quantity wins out, basically, the bigger v, because I have this squared term. I'm going to have lunch right after this. My wife is out of town. She went to a conference. So I have to have lunch all by myself. But you know what I like to have with lunch? I like those little Cokes. You ever have those little Cokes? Like the little 8-ounce Cokes? They're just the right size, right? You know where they make those? Not in Canada. Minnesota. All right. China. Okay, let's look at a 2D collision. Again, I'm not going to test you on this, but I think there's a 2D in the OpenStack. Not that hard, really, the 2D, but I do want you to see it. And then also for you MCAT folks, you might see a 2D collision. But it's really not that much more complicated. Let's see, you should have a blank page at the end of your chapter. You can just go there, and I'll just make up an example problem. Let's say that we have an object of 1 kilogram that's moving in this direction at 2 meters per second. And then we have another object that's moving, say, at 4 meters per second at 30 degrees. No, let's make it 60 degrees. At 4 meters per second at 60 degrees. And let's say that it has a mass of 2 kilograms. Now, we know that the initial momentum is equal to the final momentum. Pi is equal to Pf. But we can also say that Pix is equal to Pif. Or excuse me, Pfy. That Pix, not Pfy, Pix is equal to Pfx. And then also we can say that Piy is equal to Pfy. So we can say that the initial is equal to the final momentum, but we can also say that about the x components of the momentum and the y components of the momentum. All right, so you just add in one little step here where I can create these two separate equations. And so what I would do then is find out what are the x and y components of my momenta. So for example here, Pix would equal to 2 meters per second, 1 kilogram, plus 2 kilograms times -4 times what? How do I take the x component of that speed, that velocity? Cosine of 60, right, 4 cosine of 60. So that is my Pix. And then Piy would be equal to 0 meters per second, because this one doesn't have any y component, plus 2 kilograms times 4 sine of 60. And notice that I put that positive because the y component is up, not to the left. So that's my PIX and my PIY. And then I would set these both equal to, respectively, equal to PFX and equal to PFY. Now you need extra information here in order to solve for, say, the speed. Let's say, for example, that if this is initial, let's say that this guy, the 1 kilogram, that his final speed is equal to 0. And then we want to know what is this guy's final speed. All right, so we have 2 equations we can look at. Let's just do this one. I would have 2 kilogram meters per second minus 2 times 4 is 8 minus 4 kilogram meters per second. That's just this thing right here. And then I'm going to set it equal to PFX. PFX is going to be 1 kilogram times 0 meters per second, because I'm told that it's at rest after it hits, plus 2 kilograms times VFX. And then I would solve that for VFX, and it works out with a 2 minus 2, negative 2 over 2, so VFX is negative 1. And then you would do a similar thing where you find out what is VFY using this, and then, just like we did the vectors, you would find the resultant of those vectors and the direction. Okay? Not on the test. I'm not going to make you do that on the test. We're sort of moving past that. But I do want to just throw it out there. It's what we've been doing with 1D collisions, but you're just taking x and y components. So there's not really anything new, physics or math-wise in this. But it just makes the problems a little more difficult mathematically to solve. Okay? I think there is a 2D collision in the open stacks, and you would work it in this way. Look at the x components and look at the y components. Y'all take a look at that. If you have trouble with it, you let me know. Okay? In general, that's always true. If you have trouble with the open stacks, I'd much rather you contact me than to get it wrong. I'd really love to have 100% on those things. Okay, we're going to move on from Chapter 6. So Chapter 5 and 6 are both fairly short. On the other hand, Chapter 7 is not very short. It's actually fairly long. Fortunately, it's reviewing a lot of what we've done so far. So we're going to see kinematics again. They're not as complicated as what we did in Chapter 3. We're going to see Newton's laws again. They're not as complicated as what we did in Chapter 4 with the inclined plane and all that stuff. And then we'll also see momentum and energy. Everything that we've done up to this point, we're going to see all dumped into Chapter 7. But everything in Chapters 1 through 6 have all been moving in a line. Now, instead of moving in a line, we're going to be moving in a circle. We're going to be doing rotation. Some of y'all have done part of the lab for this, where you have the ball and make it go around in a circle. So we'll begin to see some of those things. All right. Most of it will be familiar to you. There's a little bit towards the end that will be not familiar. Okay, so we're going to discuss the rotation of rigid bodies. We'll only talk about rigid bodies. We won't talk about objects that are not rigid, non-rigid bodies. And a rigid body we define in this way, that all parts move at the same angular velocity. And whereas before we talked about velocity being a distance over time, this is going to be an angular displacement over time. So, like for example, we would measure this in revolutions per second. You might have heard that. Something spins at so many revolutions per second. That'll be what we describe as the angular velocity. So in a rigid body, every part moves at the same angular velocity. And then also, the parts do not move with respect to one another. All right, so again, we have, say this is a disk that's moving at some rate, say 1 revolution per second. Every part on this disk, this part moves at 1 revolution per second. This part also moves at 1 revolution per second. Every part moves at 1 revolution per second. So if you imagine you're spinning around at a certain rate, that's about what, a half a revolution per second? Every part on that rigid body is moving at the same angular velocity. They might be moving at different linear velocities, and we'll talk about that, but they're all moving at the same angular velocity. And then also, the parts don't move with respect to one another. So if you have a rigid body like this, the distance between 2 points is always the same. If they don't get closer together, they don't get farther apart. What's an example of a non-rigid body? Fluids are a good example of non-rigid bodies. And in fact, that's a whole other thing. And we'll talk about fluids later at chapter 8 or 9 or whatever. But a non-rigid body is like a fluid. There are whole courses that you can go on about fluid flow. It's a lot more complicated. The axis of rotation is the axis about which a body rotates. And the same body can have different axes of rotation. So for example, I can rotate my body about a bunch of different axes. Like the easiest is just to rotate if I have an axis going down through my head. I can rotate like this. Right? I can rotate about that axis of rotation. I can also rotate about this axis, right? You want to see? I don't want to embarrass you. I can rotate about this axis. I can do a forward flip, right? Some of you I know can do that. I can do it too, but I don't want to embarrass you or make you feel inferior. Okay? My daughter had a friend over, and I overheard them talking in her bedroom. They were sewing and stuff, and my daughter said, you know, my dad said that he could do a split, a full split. But he's never shown me because he says that it would embarrass me if I did it and make me feel bad. And then her friend, Mila, said, yeah, my dad says that he can do a handspring, like a backwards handspring. You know what I'm talking about? Where here you flip over. And he said the exact same thing, that he didn't want to embarrass me by showing me. It's a trick, like we can't really do those things. We're just saying that. Yeah, right. Okay, so angular position. Let me remind you just about how we get around a circle, because it is helpful for you to know this. And I think most of you do know this, but let me just remind you that in our unit circle, we have our quadrants, 1, 2, 3, and 4. That's not terribly important that you know the quadrants, but it's useful to just be able to talk about circles. We know that this is 90 degrees, 180 degrees, 270, and 360. But we also need to know those angles in radians, because we'll talk a lot about radians. Also, this can be 0 degrees. This is 0 radians. What's the 90 degree? What radian is that? Pi over 2 radians, pi, 3 pi over 2, and then this comes back to 2 pi. So this axis we can call either 0 or 360 or 0 or 2 pi radians. 2 pi radians is equal to 360 degrees. And then that's also equal to 1 revolution. We'll do some unit conversions, and you'll see some unit conversions where you have to go back and forth between radians, degrees, and revolutions. But it's just like what we did in chapter 1. All right, the SI unit for the angle, theta, is the radian. But other units, like I said, include degrees and revolutions. Even though our SI unit for theta is the radian, you'll never put your calculator in radian mode. Okay? I know y'all might do that in Calc 1, which many of you are in, but no radian mode on your calculator. So just be careful, because in fact, it'll need to be in degree mode for some of our other stuff. So on the test, just make sure that you put it in degree mode so that it knows that your angle theta is in degrees, not degrees. Even though we'll be dealing with radians, it only matters if you use a trig function. And we're not going to deal with any trig functions in the on the test. We have 2 minutes. All right, our angular displacement, delta theta, is theta final minus theta initial. This is just like what we saw before. Remember before we had delta x was xf minus xi? It's exactly like that, except now we're just talking about our angular displacement instead of our linear displacement. So for example, if I have my coordinate system and I'm going from, say, pi over 4, that's theta I, to pi over 3, that's theta f. Right, I've moved through these angles, theta, pi over 4, pi over 3. Then my angular displacement would be pi over 3 minus pi over 4, which would be whatever that is. Some positive value. I don't know what it is. Okay? And one more thing. Counterclockwise is positive, and clockwise displacement is negative. So those clocks that we have, they go in the wrong direction. Right? Because they always go in the negative direction, not in the positive direction. But y'all get those catalogs, like from the cheesy science catalogs and stuff? They sell those clocks where they go in the counterclockwise, the positive direction. You ever seen those? Bye, y'all. Y'all have a good day, okay?